And we have two types of these receptors, actually. We just mentioned them. We have rods and we have cones. And the rods are light and dark sensitive. They're very sensitive. They react to light really fast, really quickly. So we can see in the dark fairly okay. But that's why we can see in the dark, because we got those rods. The cones are the sharp ones, and they respond to color vision and to light, bright light. Because see, when bright light comes in, like daylight comes in, the rods, you can see that. You can feel that when you go from a dark room to a bright room, it's like it's blinding you. And the blinding is actually when you feel those rods flooding with light and firing all at once and then bleaching out, which means they're not firing anymore because those molecules are all straightened out. They're all just fired off, and that's it for that stimulus. And then we can see light. And then mainly what we activate are the cones at that point. So that's how we see. Straightening out molecules, 2 different types. There we go. And actually the cones come in 3 different sets, and they come in blue, red, and green, and that codes for all the colors. So if we look at color blindness, we have one of those maybe not working. That might cause you color blindness. Whew. So much for that there, right? Let's go back a little bit to the anatomy. So when we look at this back of the retina, one thing that we have this place where the nerve comes out, right here. And the optic nerve comes out. We don't have any cells there. That's just nerve coming out like that, going through it. That's a place where we cannot see. That's a blind spot. And actually, somewhere in the peripheral vision, there is a blind spot where you can't see. So if you put a dot and you move it from back to forward, somebody else does it for you, and you keep one eye closed and just look straight ahead, then you find a place where that dot disappears. Because what the brain does in an area where we don't have photoreceptors, the brain just fills it in with whatever is around it. So most of the time, it doesn't bother us at all, or it never really bothers us. So that's the optic disc. And then we have another area, actually 2 areas. It's right here. We have this brighter spot. When you look through the ophthalmoscope and you see the inside of the eye, you can see this picture right here, this one. And so in that area, that's an area where all those layers of cells, all those 3 layers of cells are basically pushed apart. They're pushed to the side. And then in the center of this, it's called the Fovea Centralis. Right here in the center, we only have have cones exposed. So we're only exposing cones. And that's a place where we have a center of gaze, where we see very, very clearly. See, one of the things that's really goofy, if you actually think of an eye, it's sort of weird. It's inverted because first the light comes in, and the light first has to go through all these cells before it hits the rods and the cones. It's like inverted. It's not like you get the light in, the rods and cones get hit, and then it moves on, and at the end of the day, the nerve just comes out, and we see everywhere perfect. It's not like that. That's one place where, we could sort of argue that maybe we could have done a different project and figured it out a little differently. But, it's okay the way it is, of course. But that's what we have. We have an area there, the Fovea Centralis, where we have the central vision, and we only have cones in there, and everything else is pushed to the side, and then that's shown sort of at the macula lutea, what's called, that yellowy part there, where all those cells are pushed to the side, that the light can penetrate straight through the Fovea Centralis. Wow. Got that? When we now look at an image that is projected onto the retina, the image is smaller, of course, the eyeball is not that big, and it's inverted from what's being viewed. And we can do that because light is being refracted. The direction of light that comes in changes whenever it goes through a curved surface. So you can see that here with the glass. You're looking at the spoon. On top here, the spoon is water. There's air. We look through air. And then we look through the glass and then the water. And look at the spoon. It looks all goofy. It's all over the place. It is multiple spoons in some areas even. And that's because of that diversion of light rays that comes to us. In the eye, the curved surfaces are mainly the cornea and then the lens. The cornea is just a given, it's just there, But the lens is moldable, so we can change the shape. We can make it flat, or we can make it rounder. Right here, see? So the lens is what focuses an image, and the image needs to be focused very, very clearly right there on the retina, not behind it, not in front of it, right at the retina. Otherwise, we don't see clear, we see blurry. So a thicker lens bends the rays more, and if an object is close, the rays coming from the object actually diverge a little bit, as compared to they're coming more parallel when the object is far away. There's just like you see an object there, but when it's really close, you only see that object, so that those rays diverge a little bit, and then of course need to be bent more sharply in order to go back to the retina, not just get then projected far back because their angle is not bent enough. I don't know if that makes sense, but that's why the round lens, when the ciliary muscle is contracted and the ligaments are taut, or laxed actually, the round lens helps accommodate for close objects. The flatter lens helps accommodate for distance, far away objects. As we get a little older, the lens becomes thicker and loses its flexibility, and we need some reading glasses as we age. I know. But also, some people have to have glasses without the old thing, because we have congenital malformation of the eyeball. So basically, what happens is the lens accommodation to the picture perfectly being projected onto the retina is out of sync. And so if we, for example, have a short globe, the picture gets projected to the farther back, and we call that farsightedness. And what we need is we basically need to bend those rays further, that the picture will be projected closer, well, not back too close, but right here, and not as far back. So we need to increase this angle. If we need to increase this angle, we want glasses that are bent this way, and that's called convex. I know those words, convex and concave, are weird. When we have too long of a globe, the image gets projected too close, not quite on the retina, but just still straight in the eyeball, inside the eyeball. And so for that, we need lenses that are curved the other way, because we need to unbend some of those rays a little bit, that they go further back to then be projected on the retina perfectly. And that unbending glass style is concave, a concave lens. I do remember convex and concave always from my spinal curvatures, and it always feels as if something's bent this way and I come from this direction. It's kind of like I'm walking into a cave. And so that's how I remember that. And then convex is just the other way around. I know, it's a bit goofy, but hey, whatever works, right? The lens is transparent because we have these proteins. They're called crystalline proteins. But the lens needs to live. And to live, we need sugar. We need ATP. And sugar is the easiest one to use for that. The metabolism of sugar, though, can change to some clumping of proteins inside the lens and making it a little cloudy, like right here, for example, a little, darkery. And that's called cataracts. And those are waterfalls when we look at the word. And I like this picture because you can see the clear vision, and then you can see the cataract vision. So you can kind of visualize what that feels like. Also, we can have what's called an astigmatism. And that is caused because when you look at the cornea, here, the normal cornea is turned nice and smooth. But some corneas are not as regular. They're like, a lot of corneas are not as regular, actually. They're like bent, curved, pointy, or something like that. And so images can be blurred and look like some things you see like a line rather than a point on the retina, and so you can get visual distortions because of that. So that's an astigmatism. When we look at measuring, figuring out, how well somebody sees, we need to measure how well the retina can differentiate two distinct spots, two distinct points at a certain distance. And so we measured that we should be able, two distinct points that are separated by 1.5 millimeter. I know. That's small. It's very small. If it's smaller than an eighth of an inch. And we have to be able to do that at about 20 feet. And so we can check that, and what we did is we created a chart that has different sized letters on them. Actually, there's also some with numbers, but the different sized letters, we can go hold one eye closed, look from a specific distance that is required or indicated on the chart, and see how well we can read. And then we can see, what kind of visions do we have? And we want to have 20/20. That means we can see these 1.5 dots at 20 feet and do really well with that. That chart is known as the Snellen chart. The Snellen chart.